that we started strongly with two field robotics activities, analog facilities, and then we are going to a more fundamental research with the talk of Dr. Raj Thilak from Delft University on AI challenge for multi-agent system in a string environment. So please.
Thank you. Thanks a lot. Thanks, Miguel. Yeah, very interesting results, right? Starting with Alex's group and then followed by Armin's group. This is going to be a little bit more fundamental AI challenges for multi-agent systems. And I'm preaching to the choir here. I think most of these challenges have been addressed by some of the members in the team, but I'll sort of motivate it a bit more because I come new to the community in robotics. I come from signal processing background. I thought I'll just introduce myself with what I do for a living. As a professor, of course, I teach some system engineering and signal processing courses, but I'm very excited about sensor fusion, distributed optimization. We'll come to that in a bit, and the need for sensor fusion, distributed optimization. And along with my team, I work on a few projects, which I'm very fortunate about. And these projects span multiple agents. So they start with rovers for the moon. They go for satellites on the far side of on the moon again, or for interferometry around the Earth, or be that drones, multi-agent drones, which have to cooperate and achieve a certain mission on Earth, right? So, and all these kinds of agents have one thing in common. You need to find the position, timing, and you want to help them navigate. But they also have to do this collaboratively, cooperatively, and this is a story that is recurring for the past few decades, right? So, and given these projects, which have agent level challenges, we also have additional projects where we look at more fundamental challenges. Assuming these agents are just point sources in Euclidean space, can I cooperatively do relative navigation? And when I say cooperatively do relative navigation, I want to find position, navigate timing without GPS and without any infrastructure, additional infrastructure, right? So that's one of the key things. Because these satellites, for instance, which are orbiting the moon, could go to the complete far side of the moon and be completely disconnected from Earth, right? The rovers which you're planning to deploy would be most likely deployed in the lunar surface without the lunar infrastructure, right? So how do you correct for their times and how do you find their positions and so on and so forth? But similar challenges also happen in terrestrial environments, like for drones and rescue missions, where you again have all the infrastructure collapsed, and how do you find PNT, but comms and processing and so on and so forth. And a combination of all these problems are not just good enough if we simulate it on MATLAB and Python and Julia, whatever your flavor is, but you also want to bring it to the sensor systems. And that's where we set up a Sensor AI lab, where we want to bring AI to the sensor system itself. And so we look at fundamental AI level challenges. So the astute among you would have realized that on the right, you have a lot more fundamental research. On the left, you have a lot more applied research on the agent. So the technology readiness of these projects span a wide spectrum of numbers, right? So, and I want to dig deep into a couple of these projects, starting with Lunar Zebra, which is just, well, it's one of the smallest rovers that we built on Earth. It's 3 kilograms. It's the size of, you know, this big of sorts. And it's got this unique C-shaped legs that you see, which is very different compared to the sort of wheeled rovers that we often see for interplanetary missions. And the C-shaped legs enables it to go over obstacles much easily. There are a couple of interesting science cases, which I think Armin touched upon already, about having interferometry, radio astronomy on the far side of the moon. And so there were studies about a rover rolling out antennas. You know, so you deploy these rovers on the lunar surface, can roll out antennas and actually do interferometry, which is a cool thing. More about this will be mentioned by Professor Chris, who will talk entirely on Lunar Zebra. But another kind of agent I want to touch upon is space-based interferometry. Again, these agents are now satellites, and they are orbiting on the far side of the moon. If I can play this video here. What you see is these satellites are orbiting on the far side of the moon, and they are doing interferometry, which is basically a combination of signals to study really early signals in the cosmos, you know, Big Bang and nearby. And what happens then is you want to have sensing of the signals and the cosmic radiations on the far side. And then once they come to the near side, you want them to communicate these signals back to Earth, right? And what happens again when they're on the far side is about 3 to 4 hours are completely blocked from any kind of Earth-based communication. And those 4 hours, how can they do detect and avoid? How can they correlate signals that they receive? How can they process? So you have a lot of these fundamental challenges. And so the big motivation for my talk essentially is that network cyber-physical systems of heterogeneous agents are not new, and we've seen tremendous amount of developments, and especially in terms of swap constraints in the last couple of decades. But what's becoming more and more intuitive, more and more clear, is that most of these agents are now deployed in inaccessible or intermittently accessible environments, right? So one of the things we're looking at is, what are the AI challenges when you do not have infrastructure to support your agents, right? So the argument is, which is pretty obvious, you need to have two kinds of behavior in AI-based systems. And one is an autonomous behavior, which leads to, in signal processing, we would call it sensor fusion. Given the amount of information that I have, how can I combine that information to have autonomous behavior to just survive and execute my mission? But autonomous behavior in itself is not good enough, because I cannot cover the spatio-temporal realm I would like to cover with just one agent. So I would need to cooperate with my other agents. And that's where distributed optimization comes into picture, right? So these two behaviors go hand in hand. And in the absence of infrastructure, again, what we would like to do is obviously take inspiration from physics. We want to take inspiration from nature. And these three sort of behaviors are inevitable in a way, right? So then what is autonomous behavior? This is an example of Lunar Zebra testing, which we are currently undergoing. So Lunar Zebra goes from point A to point B. And Lunar Zebra is an extremely small system. It's 3 kilograms, hardly has power to do SLAM, for instance. And so what it does is it relies on potential field methods, which is an extremely low cost method compared to SLAM, and goes from point A to point B. Now, this is great, but what I'm not telling you is there are anchors around the corners of the test bed, which is telling its position. There's my student standing there also correcting the time of the rover, and that's behind the black screen, right? So we have great results in terms of robust, low complexity APF methods, but there is a cheat code to it, right? And the big question is, how can I avoid this external positioning? How can I eliminate these references, right? So the fundamental AI challenges I want to push is mostly for, can we localize without anchors or GPS and GNSS? Can I navigate autonomously in an unknown environment? And can I synchronize clocks without references? This is classic ill-posed problems. In fact, clock synchronization without a reference is an ill-posed problem. But we can extend that clock synchronization to also sensor calibration. We have a lot of challenges in sensors which need to be calibrated. Cameras are being calibrated with checkerboards, and that's preposterous, because we may not have all the number of checkerboards for swarms of robots in planetary missions. But you also want to control multi-agent systems with only neighborhood information, right? Just with neighborhood information, and you want to coordinate them in multiple routes. And you also want to learn, right? So if I deploy a set of agents in an unknown environment, you want to learn that unknown environment without any model, right? So you want to do model-free learning. And many more. I can keep adding these list of challenges, but today, given the shortage of time, I'll talk about 3 key challenges, right? So, which are at different levels of mathematical maturity. I'll talk about timing without a reference, which is a completely ill-posed problem and then I'll talk about just control and learning very briefly in one slide. What do I mean by reference-free estimation, right? So timing, and when I say timing, I'm talking about time offset estimation, just because that's something that everyone understands. With multiple agents, there are 2 nodes, they exchange some time information, and from node I to node J and node J to node I, and given K measurements, you should be able to find some delay, and that's defined by D. And then there's timestamps, which is exchanged, which is measured from I to J and J to I. So typically this is represented like this. So as time progresses, node I and node J collect some timestamps back and forth. And what you see is node J has a slope, which means it's drifting away from node I. So there's not just an offset, there's also a drift. And that's sort of just an illustration of it. And this is a classic regression problem. All I do is I choose node I as my reference, and I tell node J, please follow me. And then we are synchronized, right? So this is a very well understood problem. So it's basically a regression between node I and node J, and then you subtract them, and plus minus, depending on you're going up or down, you have a closed form equation, which you can solve through least squares, lasso, and whatnot, right? So this is a decade-old problem. But the big question is, what if these nodes are mobile, right? So now they are not fixed. The distance is going to change. And then I also don't have a clock reference. I do not know who my clock reference is, right? So now this becomes exciting. So then the story continues. It's the same node I, node J. You still want to have the same pair of equations. But now the illustration becomes a bit interesting. So you have a curve because both the time and the distance are interplaying with each other. And there's no shaded block here because I do not know which one is the reference. I have to figure out who's the good reference to do. Equation remains the same. There's clock I minus clock j, but now there's this complicated function because both your distance and time are connected to each other. Can I decouple that is the big sort of AI challenge that we face, right? And fortunately, we can solve that. And that's essentially a one-slider that we can say we can choose a single clock reference, or we can do some sort of a mathematical average between all the 4 nodes and say, please follow the average, and I can guarantee you converge to this average value. And that's something that we can claim is optimal for both offset and drift. And then instead of the average, we can also do a bit more statistically optimal sort of clock choice. And what these sort of statistical algorithms do is then they give you optimality, they give you assurance that if there is one of these sensors which have failed and have a wrong clock, compared to that, these 2 algorithms will do much, much better, right? So that's the whole game. So you avoid single point of failure for a thing like clock, and you rely on the information of the swarm. And here I, of course, illustrate for n equals 4, but if you expand these number of agents, obviously you'll have a bit more, much more accurate clocks, right? So that's the game. And the usual plot of you have accuracies and information on the x-axis, and as you have more number of measurements, you get better improvement. But you see these triangles in the top are the state of the art, and then by averaging, you sort of having an average reference, you go lower and lower, and you get much better results. That's the whole thing. And if I can use time, I can also use frequency. And if I use frequency, for instance, I get even more lower results, and that's the whole game, right? So we can sort of have this average clock reference and sort of show that we have much more accurate clock synchronization. That's great for clock synchronization, but I just want to show one slide about control. How can I do distributed control? I have a bunch of agents, and I want them to achieve a certain formation. And this is important in interferometry, polarimetry, and many kinds of formation control problems. And I don't want to have a centralized correlator. I want a centralized processor. I want to have only neighborhood communication, right? So fortunately, there's nice models in control theory where I can only talk with neighboring agents, and I can sort of swarm to sort of achieve a certain configuration, right? And when I do that, I can, that's not just enough. I also want to change this formation, right? And that's leading towards flocking behavior. And that's exactly what we try to do here. We go from some arbitrary position and we try to look at geometry of the problem to have more distributed formation control. Right, so, and then the third topic is on learning, for instance, where I do not know a model. I have deployed a bunch of agents. In this case, this is Lunar Zebra, which is on the far side of the moon. It has to measure some field, and I don't know what field it's measuring. It could be radiation, it could be temperature, it could be humidity, pick your flavor. And I don't know this field. And so this is a mathematical problem where you have sparse bunch of agents which are arbitrarily connected, and they want to measure this unknown field below. And what we can do is do distributed non-parametric Bayesian models on these kind of topics. So then we have nice plots, which basically sort of say we can, with a lot of iterations on the x-axis, a lot of communication between the nodes, we can sort of estimate the entire field for the whole area, right? So that's just a glimpse of problems which are completely ill-posed, like clock synchronization, and problems which are relatively understandable, like distributed optimization and learning in multi-agent systems that we try to tackle in our group. And so I just want to summarize, heterogeneous systems have been there for a long, long time, but I feel that the big AI challenges, especially if we want to compete with ChatGPT era, you want to look at ill-posed problems that you can solve. And I think these things rely heavily on external infrastructure. You want to mitigate that external infrastructure. And so that's where intelligence can help us. And that's where I'm very excited about. And so those are some of the challenges that I just give a brief overview of. I'll be happy to talk to you in person about any of these topics if you're excited. Thanks a lot for your time again. Thank you.